Hi everyone, this chapter is about the attraction and repulsion of two magnets. First of all, let's take a look at a bar magnet like the one used in many schools for student experiments. Such magnets usually have two colors, in this case red and green. This marks the two poles of a magnet. The north pole is colored red and the south pole is green. The aim of this experiment is to find out what happens when the poles of two magnets approach each other. When the south pole of one magnet is brought close to the north pole of a second magnet, an attractive force acts. The same applies if the north pole of one magnet is brought close to the south pole of a second magnet. Two identical poles, the south pole and the south pole, or the north pole and the north pole, repel each other. In the following experiment, we investigate the question of how to make a magnet from an ordinary iron nail and then demagnetize the magnetized iron nail again. First, I try to pick up an iron paperclip with the iron nail. As you can see, with rather moderate success. Here the whole thing again in the animation. To get an idea of why you can't pick up a paperclip with a non-magnetized iron nail, let's take a look inside the nail and the paperclip. First, let's look at a self-made model of an iron nail. Let us assume that there are a lot of small bar magnets in the iron nail to explain why an ordinary iron nail has no magnetic effect on the outside. These small magnets are called elementary magnets. However, this is only a simplified model and not the actual structure of a magnet. The elementary magnets are arranged in such a way that as many south poles as north poles point in all directions. As a result, the magnetic forces balance each other and the iron nail has no external magnetic force to attract the paperclip. A look inside the paperclip shows us that the elementary magnets are also aligned here so that the paperclip has no magnetic effect on the outside. Let's go back to the real experiment. You see that a magnet can be used to lift an iron paperclip. What's the difference between a magnet and our iron nail? Let's look at the structure of a magnet in the model. As you can see, in the bar magnet, more north poles of the elementary magnets point downwards than upwards. This unequal alignment of the elementary magnets ensures that the bar magnet has a north pole at the lower end. The magnetic force of the north pole now ensures that some elementary magnets in the paperclip are aligned with their south pole facing up. The north pole of the magnet and the newly created south pole of the paperclip are now facing each other. And as you already know, unequal magnetic poles attract. Now I stroke the iron nail with the north pole of the magnet always in a certain direction. Now I can lift the paperclip with this iron nail even if it would not have had contact with the bar magnet before. What happens when the magnet is swept over the iron nail? Let's look at this in the animation. The north pole of the bar magnet with its magnetic force ensures that some elementary magnets in the iron nail align with their south poles towards the north pole of the bar magnet. Now in the iron nail, more elementary magnets point with their south pole downwards than upwards. The nail thus has a magnetic south pole at its tip. the south pole of the nail and the north pole of the bar magnet attract each other. Even if the bar magnet is now removed from the iron nail, the orientation of the elementary magnets in the iron nail remains, so that the nail still has a north and a south pole. Now you can lift the paper clip with a magnetized nail. Now I hold the tip of the iron nail in the flame of a candle for a long time and try again to lift the paper clip with the nail. As you can see, again with moderate success. What happens to the magnetized iron nail when you hold it in the candle flame? First of all, the elementary magnets are aligned so that more south poles point towards the tip. However, the warmth of the candle ensures that the elementary magnet starts to move and align themselves so that the same number of south and north poles point towards the tip of the nail. As a result, the iron nail again appears non-magnetic to the outside. The iron nail was demagnetized. It is no longer able to pick up a non-magnetized paperclip. This chapter is about the magnetic field. Let's first look at an experiment. A bar magnet is hung on a thread. This can rotate freely. Before starting the experiment, the south pole of the bar magnet points to the right and the north pole to the left, as seen from us. Let's see if we can change this direction. To do this, I turn the bar magnet so that the south pole and the north pole point in a different direction. After I let go of the bar magnet, it starts to turn back and forth. It takes so long that I'll show you this in a fast run. Only after I move the bar magnet back into position so that the south pole is pointing to the right does it stop rotating. This is the only stable alignment. But why? I removed the bar magnet and put a compass under the clothespin. The compass shows us in which direction the north and south poles of the Earth are. We remember that the south pole of a bar magnet pointed to the right, where according to the compass the south pole of the Earth is. That's strange. We had found in an experiment that two identical magnetic poles repel each other. To explain this, we need to take a look at the Earth. As you probably know, the Earth rotates on its own axis. Let's position a huge compass on the Earth. The compass needle is nothing more than a bar magnet with a north and a south pole. The north pole of the compass needle points in the direction of the north pole of the Earth, and the south pole of the compass needle points towards the south pole of the Earth. How can we explain that? The Earth has two magnetic poles like a bar magnet. Let us imagine that the Earth rotates around a huge bar magnet. The decisive factor is that the bar magnet at the geographic north pole has a magnetic south pole. At the geographic south pole it has a magnetic north pole. This explains why our freely rotatable bar magnet pointed with its north pole to the geographic north pole, and this was attracted by the magnetic south pole. However, our magnet is very far away from the magnetic poles of the Earth. How does the magnetic sense where north and where south is? This has to do with the magnetic field around the magnet. Let's take a step-by-step look at what the shape of the magnetic field of a bar magnet looks like. To do this, I first put a compass around the bar magnet. The compass needle aligns itself with the bar magnet depending on its position. The tip of the compass needle is the magnetic north pole. This points in the direction of the magnetic south pole of the bar magnet, and the flat end of this compass needle points in the direction of the north pole of the bar magnet. If you take a lot of small compass needles instead of a single compass needle, the following picture emerges. You can see lines that point from the north to the south pole. If you change the alignment of the bar magnet, the alignment of the compass needles also changes, so that we can again see lines that point from the north to the south pole. The shape of the magnetic field can be illustrated even better by placing a white cardboard over a bar magnet and sprinkling small iron fillings on the cardboard. You can see 2 points at which many iron fillings are arranged. Below these 2 points are the end of the bar magnet. The magnetic force is strongest there. Starting from the 2 poles of the magnet, the iron fillings are arranged in straight and curved lines. Let's look again in the animation at the examination of a bar magnet with several compasses. If you now connect the alignment of the individual compasses with lines, you get the following picture. Here you can now see the shape of the magnetic field around a bar magnet. The individual lines are called magnetic field lines. These magnetic field lines never intersect. The direction of each magnetic field line is shown with a small arrow. Internationally, scientists have agreed that the magnetic field lines point from the North Pole to the South Pole. The direction of the magnetic field lines is not very important at this point, but it is helpful to know in later lessons if, for example, you want to determine the direction of the Lorentz force. The density of the magnetic field lines, that means the number of magnetic field lines in a certain area, indicates how strong the magnetic force is at this point. At the 2 ends of the bar magnet, the magnetic field lines are very close together, since all magnetic field lines exit from the North Pole and enter the South Pole. Accordingly, the magnetic force is greatest there. To the side of the magnet, the magnetic field lines are not so close together. The magnetic force is also significantly lower here. Next to the bar magnet is a so-called horseshoe magnet of particular importance. If you examine the shape of the magnetic field of a horseshoe magnet with a compass, you will find that the orientation of the compass in the center of the horseshoe magnet is the same everywhere. You can see this even more clearly if you use our many small compass needles again. Only in the outer area of the horseshoe magnet do the compasses show in different directions. The magnetic field of a horseshoe magnet can again be illustrated very nicely with the help of iron fillings. In the animation, let's look at the orientations of the compasses and the magnetic field of a horseshoe magnet. In the middle, the orientation of all compasses is the same. In this area, one speaks of a homogeneous magnetic field. In this homogeneous magnetic field, the magnetic force is the same everywhere, both in its strength and in its direction. There's an inhomogeneous magnetic field around the horseshoe magnet. This video is about the connection between electricity and magnetism, the so-called electromagnetism. The so-called Oersted-Experiment can be used to show this connection experimentally. To do this, you place a compass under a power cable in such a way that the compass needle is aligned parallel to the power cable. As long as no current flows through the power cable, the compass needle points towards the 2 poles of the Earth. However, if you turn up the voltage of the power supply unit, electric current flows through the power cable. The compass needle is now aligned perpendicular to the power cable. In addition, it can be shown that the higher the voltage on the power supply unit, and thus the current, the more the compass needle is influenced. Let's go in the animation to imagine how the compass deflection occurs. Also here it is shown that the compass needle aligns itself perpendicularly to the power cable as soon as current flows through the power cable. Let's take a look inside the power cable. A power cable is made of many atoms. We are only interested in specific electrons in the power cable. As long as the voltage at the power supply is zero, no current flows. If you turn up the voltage, the electrons start to flow towards the positive pole of the power supply. The higher the voltage, the faster the electrons flow and the more the compass needle is influenced. It is important to note that the electrons in this case are oversimplified. The electrons, drawn as small spheres, are used here to show the number of electrons that pass through the transparent part of the power cable in a given time. The reason the compass needle is affected is a magnetic field that forms around the power cable as the electrons move. This magnetic field is stronger the faster the electrons move in the power cable. For a small area very close to the power cable, the magnetic field is stronger than the Earth's magnetic field at that point. Therefore, the compass needle is deflected according to the magnetic field around the power cable. It is important for further understanding that we can show at this point that the origin of magnetism lies with the electrons. Moving electrons create a magnetic field. This chapter is about the magnetic field around a current-carrying power cable. In order to visualize the shape of a magnetic field around a current-carrying power cable, I carry out the following experiment. You see a power supply unit to which two power cables are attached. The two power cables are connected to each other so that we find a large electrical circuit. Without any resistance, we create a short circuit for a short time. So you should be careful not to leave the power supply switched on for too long and not to set the voltage too high. In the experiment, the electrons will flow from the blue negative pole of the power supply unit up through the blue cable and down through the red cable to the positive pole of the power supply unit. If you examine the magnetic field of a current-carrying conductor with a compass, you can see that the compass needle orients itself differently depending on its position in relation to the power cable. The electrons flow up through the blue power cable. Behind the power cable, the tip of the compass points to the right and in front of the power cable to the left. On the other side, the electrons flow downwards. Here, the tip of the compass points to the left behind the power cable and to the right in front of the power cable, so exactly the other way around. To explain this, let's have a look at the whole thing again in the animation. Here again the direction in which electrons flow. The electrons are repelled by the negative pole of the power supply unit and are attracted by the positive pole of the power supply unit. If you connect the individual compass needles, you get a circle. In contrast to the magnetic field of a magnet, the magnetic field around a current-carrying cable has no north or south pole. The tips of the compass needles indicate the direction of the circular magnetic field lines. There's a trick to determine the direction of the magnetic field lines. To do this, place your left hand around the power cable as shown in the animation. The thumb points in the direction in which the electrons flow. The remaining fingers then indicate the direction of the magnetic field. This chapter is about the question of what the magnetic field looks like around a current-carrying coil. On the right side of the table, we examine the magnetic field of a bar magnet with the help of a compass. On the left side, there is a coil that is connected to a power supply unit. If we switch on the power supply and we increase the voltage, current flows through the coil. Now we can examine the magnetic field around the coil with a compass here too. In the animation, we compare the different orientations of the compass needle at different positions around the bar magnet and the coil. We find that the magnetic field around a bar magnet and the magnetic field around a coil have the same basic shape. So, if current flows through a coil, you can easily imagine that you are holding a bar magnet in your hand. How does the shape of the magnetic field around the coil come about? Let's take a look at the flow direction of the electrons through the coil. The electrons flow from the negative pole of the power supply unit into the upper side of the coil. Then they flow in a circle 600 times until they flow over the red cable to the positive pole of the power supply unit. Let's take pieces of wire out of the front of the coil as an example. From our point of view, the electrons flow upwards through the front. To determine the shape of the magnetic field, we use the left hand again. The thumb points in the flow direction of the electrons and the remaining fingers indicate the direction of the magnetic field. All wire pieces on this front side form a magnetic field with the following simplified form. Now the magnetic fields come through the other sides of the coil. Together, this results in a three-dimensional magnetic field of a bar magnet. This chapter is about a special form of magnetism, namely diamagnetism. I've chosen the following experiment to show you the effect and its effects. For the experiment, you only need 4 neodymium magnets and a piece of graphite. If you position the graphite piece in the middle of the magnet, it will float. The repulsive force between the magnets and the graphite is so great that you can weigh down the graphite plate with cotton swabs. Let's look at the structure of the experiment again in the animation. To explain to you why the graphite floats on the magnet, I'll show you another experiment. For this experiment, I cut out the bottom of a tea light so that only an aluminum ring remained. I attached this ring to a tripod rod with 2 threads and a little sticky tape. I also need a permanent magnet. I'll show you briefly that this is a magnet. Hopefully, in slow motion you can see that the aluminum ring is repelled by the magnet as long as I move towards the aluminum ring with the magnet. The question is, what happens in the aluminum ring when the magnet approaches? To do this, we switch to the model level. The small dots in the aluminum ring are supposed to represent some free electrons in the aluminum. As soon as I approach the magnet, these electrons move in a circle. This effect is called induction, and it only occurs with electrical conductors. The direction of the induced current is now decisive. As the magnet approaches, the electrons move in such a way that they generate a magnetic field that is opposite to the external magnetic field of the bar magnet. In this case, the south pole of the bar magnet and the south pole of the magnetic field of the aluminum ring through which the current flows are opposite. However, since the free electrons do not move without friction in the aluminum, their movement stops as soon as I do not move the bar magnet any closer to the ring. This also causes the magnetic field around the aluminum ring to disappear. But what does this experiment have to do with our graphite? If you take a closer look inside the graphite, you will find electrons there that are bound but not localized. These are so-called pi electrons. An external magnetic field now ensures that these pi electrons form circular currents. The direction is such that the circular currents form a magnetic field that is opposite to the external magnetic field. Important, these are not induced currents, but this form of magnetism is called diamagnetism. So here too, there are 2 poles of the same name, in this case the south pole and the south pole, facing each other. This leads to a magnetic repulsion. However, since the pi electrons can move without friction, their movement does not stop and the magnetic field caused by the circular currents is retained. If you take a closer look at the neodymium magnets, you will see that the following arrangement is present. 2 of the neodymium magnets point with their north pole and 2 with their south pole in the direction of the graphite plate. As a result, 4 areas are created in the graphite plate, because in each area a magnetic field opposite to the underlying magnetic field of the neodymium magnets is generated. The individual areas of the graphite plate therefore experience a resulting force that points into the center of the 4 neodymium magnets. A look at the underside of the graphite plate shows once again that 2 poles of the same name are facing each other and that this is the reason for the floating graphite plate. This chapter is about the 4th form of magnetism, paramagnetism. In the following experiment, an aluminum foil is folded over a thread. If you approach the aluminum foil quickly with strong neodymium magnets, it is first repelled by the neodymium magnets. So is aluminum foil also diamagnetic? If you first approach the aluminum foil with the neodymium magnets and then pull the magnets away, the aluminum foil is carried away. So does the magnet attract aluminum after all? What you see here is the same as what you see in the video about diamagnetism with the aluminum ring happened. If you approach the aluminum foil with a magnet, circular currents are induced in the aluminum. The direction of the circular currents is such that when approaching, a magnetic field is created around the aluminum, which is opposite to the neodymium magnets. Thus, in this case, there are two south poles facing each other, which repel each other. If you remove the neodymium magnets from the aluminum, the direction of the eddy currents is reversed, so that the south pole and the north pole now face each other and the aluminum is attracted by the neodymium magnet. However, if you keep the neodymium magnets at a constant, very small distance from the aluminum foil, it will be attracted by the magnets. When aluminum is attracted, it cannot be circular currents that are responsible for it. The reason here is in the spin of the electrons. This is the missing magnet form of expression, the paramagnetism. Without a magnet nearby, the spins of the electrons in aluminum are oriented almost arbitrarily in all possible directions. If you now approach a strong neodymium magnet, a few spins of unpaired electrons orient themselves in such a way that the majority of the magnetic moments of the spins are now aligned in such a way that they are attracted to the south pole of the neodymium magnet. This video is about the Stern-Gerlach-Experiment. In this experiment, silver is heated so much in a furnace that it becomes gaseous. A few individual silver atoms leave the furnace through a small aperture in the direction of an inhomogeneous magnetic field. Behind the magnetic field there is a photoplate which the silver atoms hit and leave an imprint. The result is that the silver atoms are deflected either up or down. Some of you might now think that the distraction is due to the Lorentz force. However, these are not positively or negatively charged particles that fly through the magnetic field. They are complete silver atoms with an equal number of protons and electrons. Therefore, no resulting Lorentz force acts on the silver atoms. Let's take a closer look at the silver atoms. A silver atom has 47 electrons. The electrons are at different energy levels. It is already noticeable that there is an even number of electrons at every energy level. Only one is at the highest energy level. Let's take a closer look at the electrons. The Pauli principle states that no two electrons on a shell may have completely the same quantum numbers. The main quantum number indicates the shell on which the electron is located. In simple terms, the distance between the electron and the atomic nucleus. Let's start with the two electrons on the K shell. The secondary quantum number, SPDRF, indicates the shape of the orbital in which an electron is located with a probability of 90%. The magnetic quantum number, M, indicates the orientation of the orbital shape. At first glance, one might think that the two electrons on the K shell are the same in all quantum numbers. But according to the Pauli principle, they are not allowed to do that. However, if we take a closer look at the two electrons, we notice a difference. The final missing quantum number of an electron, the spin, is what differentiates these two electrons. The left electron has a spin down and the right electron has a spin up. These two electrons, which have completely identical quantum numbers except for the spin, are called paired electrons. If you look at the electrons on the other shells, you can see that they consist entirely of paired electrons. Only on the highest shell there is a single unpaired electron. This electron can assume both spin states, spin down or spin up, without breaking the Pauli principle. Now let's go back to our experiment. As already mentioned, whole silver atoms always fly through the magnetic field. Now let's look at what happens to all 46 paired electrons as they fly through the magnetic field. The spins of the two electrons must be opposite at all times. Otherwise, they would break the Pauli principle. Before entering the magnetic field, the spins are oriented in all possible directions. When entering the magnetic field, the spins align with the magnetic field. In this case, the spin of the left electron points in the same direction as the magnetic field, and the spin of the right electron points in the opposite direction. An atom that consists only of paired electrons is not deflected in the magnetic field. But the silver atom has an unpaired electron. If this enters the magnetic field, it aligns itself either in the direction of the North Pole or in the direction of the South Pole. The most important thing is the alignment before entering the magnetic field. If the alignment is previously directed towards the North Pole, the spin is in most cases completely aligned to the North Pole. In this case, this unpaired electron experiences an upward force. It can thus be shown that the spin of the electron has a magnetic moment and is either attracted by the North Pole, as in this example, and repelled by the South Pole and deflected upwards, or, as in the second example, exactly in the opposite direction.